All right, good morning, students. I hope we all doing great. Everything is copacetic, and I am sorry for yesterday we could not meet, but let's try and make it up this morning. Okay, so this is the continuation of operating system memory management. And this is part two, and we're going to look at dynamic storage allocation problem. So when it comes to dynamic storage, we have the first fit, we have the best fit, and we have the worst fit. Now, the first fit, it allocates the first hole that is big enough to fit the process. Okay. So what happens is that the process is fit into the first hole that is big enough. So if your process is, let's say, 2 KB, and the first hole you find is 4 KB, it allocates that location to the process. But the problem here is because the process is 2 KB, that is 2 kilobytes, and we have 4 kilobytes. Once we fit there, the 2 kilobytes become waste. Okay. Then we have best fit, and best fit allocates the smallest hole that is big enough. So it must search the entire list unless ordered by size. So, for instance, we have 2K to 2 kilobytes. The process has 2 kilobytes, and the first hole you find is 4 kilobytes. It will search the entire thing. Then you'll realize that there is a hole that is maybe 3 kilobytes, and that is the smallest. And 3 kilobytes is a little more than 2 kilobytes, and it will fit the process there in memory. Then we have the worst fit, and the worst fit searches the entire list and it picks the largest hole. So it searches the entire list. So again, you have this process that is 2 kilobytes. So you look at the first hole is 4 kilobytes, next hole 3 kilobytes, the next hole is 6 kilobytes. So it'll check throughout the list and it'll realize that the 6 kilobytes is the largest, and it's going to fit the 2 kilobytes process into the 6 kilobytes. And that you see the problem there too. We have 4 kilobytes that is wasted. You see. So first fit and best fit better than worst fit in terms of speed and storage utilization. So first fit and best fit is much it fits it's better, it works better in terms of speed and storage, okay? Because the worst fit goes for the biggest hole. So if your process is even 1 megabyte and it goes searches through the list and it finds the biggest hole is 10 megabytes, it's going to allocate the 10 megabytes to that process that is 1 megabyte, and it means that 9 megabytes become waste. All right. So in this sense, um, we have fragmentation, and we have external fragmentation and internal fragmentation. All right. Now, we might want to look into the meaning of fragmentation. Okay. So, what is fragmentation? It is it is when free memory is broken down into small, non-contiguous blocks. So, it is broken into non-contiguous blocks, and it makes it difficult to be able to allocate a huge size of memory to the process despite having enough total free space. So there you have it. That is fragmentation. Yes. So when we say fragments, you just look at the word, it's broken into fragments, into different pieces, but it's broken into different memory blocks, which is non-contiguous, which means I told you that arrays are contiguous. So this is non-contiguous. All right. So external fragmentation, the total memory space exists to satisfy a request, but it is not contiguous. All right. Then internal fragmentation, the allocated memory may be slightly larger than the requested memory. Yes. Um, this size difference is memory internal to a partition but not being used. So it's somehow wasted. So we say first fit analysis reveals that given n blocks N is arbitrary, okay? Um, N blocks are located. 0.5 N blocks are lost to fragmentation, okay? So one third of it, the memory may be unusable. Now, how do we reduce fragmentation? There is one method called compaction. And what does compaction do? It shuffles the memory content to place all free memory together in one large block. So compaction is possible only if relocation is dynamic and it is done at execution time. So what happens is in this memory, we know that there is this non-contiguous form, okay? So this non-contiguous form creates fragmentation because you have a process that covers a certain size, but there'll be extra memory available. So what happens is that this memory that's available ends up being waste. So what we are supposed to do is we are supposed to use compaction to solve this problem. What compaction does is it takes all this memory that is not being used, that is the waste memory, and it compacts it together and places it as one large block. Okay. All right. So back to this backing store thing. Some books I read, they told us that the backing store is the secondary storage. But actually, I went into details, and the backing store, you see, so if you look at virtual memory, for example, virtual memory is a part of the secondary storage, which is used to compensate main memory. And you can say virtual memory is a backing store. So a backing store is an area whereby these processes are swapped in and swapped out. Yeah, because it makes sense because if it is to be secondary memory, getting a program from secondary memory, putting it back in there, it takes a lot of time because we know that if you look at the memory hierarchy, we know that the secondary storage holds a lot of has a large volume of space, but it is very slow. So it doesn't make sense that the backend store has to do mostly with a portion within the virtual memory. Okay, so segmentation is a memory management scheme that supports user view of memory. So we know that a program is a collection of segments. And what do we mean is a logical unit, such as in the program, we have the main program, procedure, the functions, we have the methods, we have objects, we have the local and global variables, we have the stack, and we have this symbol table. And if possible, we have arrays. All right. So this is the view, a user's view of a program. So you see this program now is a process because we are seeing logical address. So it has a symbol table, a subroutine, has a stack, main memory. Yep. So this is how the logical view of segmentation would look like. So you see that in this user space from this program here, right, which has a logical address, you see each one of these, which is subroutine, stack, symbol, main program. So you have one, two, three, and four. But look at how it is placed in memory. You have one and four, then this other shaded area is memory that becomes waste, is not used. You have two and three. Shaded area is memory that becomes waste. And this is non-contiguous because if it was contiguous, you have one, two, three, four, all one following the other. So this is a form of non-contiguous. So that is the physical memory space and how it is located in the memory space. So logical addresses consist of two tuples. Consists of what? The segment number, and it consists also of the offset. And what is an offset? The offset actually specifies the location of a specific piece of data relative to a base address. So logical address is equals to segment base address plus offset. So what do I say again? I say offset specifies the location of a specific piece of data, okay, with relations to its base address. All right, so a segment table it maps 2D physical addresses. Each table entry has a base or base address containing the starting physical address where the segment resides in memory. So unlike where we had the logical addresses, we had the situation of you have the base register and the limit register. You see, so this is the base here again. It says contains the starting physical address where the segment resides. Limit address specifies the length of the segment. Okay. And over here we are talking about physical address. Okay. So segment table base register points to the segment table's location in memory. So it is a pointer. Yes, STBR is a form of a pointer, and it points to the segment table's location within memory. Then you have the segment table length register, and it indicates the number of segments used by a program. Okay. All right. So with protection, when it comes to segmentation architecture, with each entry in segment table associated, validation bit is 0. That is an illegal segment. And you can, the privileges are you can read, write, and you can what? Execute. So RWX. Protection bits associated with segments, code sharing occurs at the segment level. All right, so let's skip this. Let's go to paging. Physical address space of a process can be non-contiguous. Yes, it is true. Processes are located physical memory whenever the latter is available. And it does that to avoid external fragmentation and the variant size of the memory chunk. So what is paging? Paging happens when a demand is being made for a process to be swapped in to memory or swapped out of memory. Okay, so physical memory in fixed blocks called frames. So we're saying that secondary main memory is divided into frames, right? And secondary storage is divided into sectors. Yes, and you have virtual memory is divided into frames, the same thing. So uh, basically, logical memory is divided into blocks of size called pages, and what the size of a page is equals to the same size of a frame. So if you take a main memory, which is divided into frames, then you take your virtual memory, which will be divided into pages, because you see, a process is divided into pages. So a process, depending on the size of a process can use more than one page, but a page and a frame carry the same size. Okay, and it is in the power of twos. Okay, it's in the power of twos. So to run a program of size n pages, you need to find n free frames and load the program. And it sets up a page table to translate the logical address to what's the physical address. We saw that when we looked at the relocation register. So yeah, so we use the page table to be able to map the logical address to the physical address. Okay, and the physical address is within your main memory, and you have the logical address which is generated by the CPU. So the backend store likewise splits into pages. So the backend store is also divided into what pages. So that clarifies the point I made about virtual memory. Yes. Okay. Address translation. Address generated by CPU is divided into what? You have the page number and you have the page offset. Okay. Let me just move this so we can. Okay. So the offset is what combined with the base address to define the physical memory address that is sent to the memory unit. So just look at it this way. The offset indicates the size. So as we saw in the limit register, you see you have the size. So if you add the base address to the contents in the limit address, you're able to get the range of addresses the process can access exclusively. All right. All right. So this is the paging hardware, and you have the page table. So you have the logical address, and there is the physical address. So it's just mapping the logical to the physical, and we know that the logical address is generated by the CPU. Okay. So you have page 0 in logical memory, and look at the page table here. So you have page 0, right? So it is telling us that um, page 0 is in location 0 in logical memory, but it is in location 1 in physical memory. Now look to your right, you see, so you have the frame number. Yes, you have the page number, then you have the frame number. And that is how the page table exactly works. All right. All right. So we're going to skip this. Most of this is for postgraduates. So I am trying to keep you guys on yours. Yes, these are postgraduates. Yes, so I think we will leave it here. Yes, we are going to leave it here. And so far we know about memory. We know the types of memory that is internal and external, which we did. We also studied in computer organization architecture. We know about how memory is managed and how address spaces are protected by the help of the base register and the limit register. We know about how logical addresses are generated by the CPU. And we said that main memory is divided into frames and virtual memory is also divided into pages. And the size of a page is equals to the size of a frame. Okay. We looked at fragmentation and we saw the problems that come with fragmentation because there ends up being non-contiguous memory allocation. We said we can use things like compaction to be able to solve that problem. And we further looked at the page table, saying the page table is used to map the logical address to the physical address. Okay. All right. So I think we will leave it here and let's consider memory management done. And I'll see you in the next class. Thank you.